All right, here we go. We're in section 1.2. We're going to be talking about initial value problems, and we're going to introduce and just take a look at the existence and uniqueness theorem. We won't go through any of the proofs or anything, but we'll take a look at it, and then we'll probably be able to jump to section 1.3, which will be actually solving for some differential equations. So this is still some more introduction with our differential equations and still getting to know it. So a definition that we're going to be using a lot is IVP. We have to know what that is. And an IVP is an initial value problem. So an initial value problem is a differential equation that has initial conditions. And initial conditions are conditions that are given on the particular function that you're trying to solve for. And the conditions are usually given at one particular independent variable value, a specific x value. If your independent variable is x, sometimes it's t, sometimes it's something else, but there's a specific value, and then you're going to have a set of conditions. Now, if you look at this, this is an nth order differential equation, and how many initial conditions are we looking at? Can you read this? Is this too mathy for you? Yeah. Yeah, so there's these conditions, there's these n-1 conditions from the first derivative to the n-first derivative, and then there's this original function condition, so that's a total of n initial conditions. Yeah. I don't know. No, there should be n equal signs. Yeah. Because there's 1, and 2, 3, 4, etc., and then n-1, and then there's this extra one over here, where sometimes we consider it the 0th derivative if we're talking about the original function without taking the derivative of it. So for all you computer programmers, everything starts at 0, right? So 0 to n-1, there's actually n of them. And we should have probably focused on an example last time and actually solve for it, because there's a couple of things that we can solve for already. One of them is the let's not use E, let's use something else. So this is a differential equation, and this is a first order differential equation. So if I want this to be an IVP, I would make up, or I would come up, or the problem would have one initial condition, because this is a first order. So let's say at 0, this is equal to 2 or something. And if we temporarily ignore this initial condition and go ahead and solve for this differential equation, we would integrate both sides, so to speak, as an indefinite integral. What's the antiderivative of 2x? X squared plus c, right? Now, if you look at this from last time, if you remember some of the solutions that we have one parameter, 2 parameter family of solutions. So the number of arbitrary constants we come up with is the number of parameters we would have. In this case, we have one parameter, and so we probably saw this graph back in Calc 2. We have a bunch of different x squareds plus c's, depending on what c is equal to. Say c is equal to 0, c is equal to 1, c is equal to -1, etc. Then you'll have these parameters, family of solutions, family of curves that would describe the solution. Okay? So now if you insist on an initial condition, then that means you get to put your initial condition of x value and the y value into your parameter, so you can try to figure out which one of these curves you should be looking at for your specific solution. So if we put y is equal to 2, x is equal to 0, we can get an idea of which one of these families of curves we're looking for, or not families, which one of these particular curves we're looking for out of the family of curves. So it looks like c is equal to 2. Let's try that again. So this is the particular solution you're looking for. So this is an example of an IVP, initial value problem. We have a differential equation, an initial condition, and then with that we should be able to get one solution. And that's what the next theorem is going to tell us, is that if we have an IVP, complete set of initial conditions for our differential equation, then we're going to be guaranteed a solution, and we're going to be guaranteed that that solution is the only one that exists for this particular problem. Now, I don't know if I want to jump ahead a little bit, but this is probably something that you might have seen, just as another example. Let's just put y. This is another example of initial value problem. Anybody know what this might, what the solution of this might be? Yeah. Yeah. So if we look at it carefully and say the derivative of a function is equal to the original function, does that sound familiar? So what function has a derivative that exists and it's equal to itself? Yeah, and then if we put another number here, we could ask the same question. What's the derivative of a function is equal to itself, maybe times a constant, or we would say proportional to itself. And it's still an exponential function with an added constant, right? So this is another example. And if you look at the type of family of curves this has, it's not the plus c that we see on the outside that would shift your solutions up and down. It's going to do something else. It's going to have a multiple. Anyways, so your guess might be y is equal to e to the k x. Right? But you got to ask, well, is this really the solution? And usually when we don't incorporate your initial condition, we would have a family of solutions. And I kind of don't see the family of solutions here yet. In fact, if we were to plug in, k is a fixed number, by the way. Let's just put, can we just put 5 there? Let's just put 5 there. So the question is that, is this really the solution? And when we put 0 in for x and 3 in for y, we're going to get e to the 5 times 0. And so we're not going to get the correct answer. So that means we need to somehow generate a family of solutions for this before being able to use the initial condition. So let's leave this as a question mark right now. And by the end of the day, we should be able to get to section 1.3, which talks about separable differential equations, and we can easily solve for this. But it has something to do with exponential functions, so let's keep that in mind. Okay. So the next thing that we want to look at is the big theorem for differential equations. Like when you're solving for things, how do you know that you're actually going to come up with a solution? And if you do come up with a solution, are there any more solutions, or is that the only one? So that question comes up in a lot of cases in math, and especially in differential equations. And in differential equations, it's called the existence and uniqueness theorem. And here they talk about some rectangular region. They talk about some intervals for x and some intervals for y that make up your rectangular region. And it contains some initial point, initial value. That's the initial conditions that we're going to be looking at. Now, I know we're not assuming that you've done Calc 3 and you know about partial derivatives and stuff like that, but a partial derivative is really just, if you take a look at a function that has two variables x and y, then a partial derivative is just a derivative of that expression where you hold one of the other variables constant. You pretend it's a constant. So we're assuming that we have f of x, y, and the partial of this function with respect to y are continuous. And then it says that there exists an interval, there should be an interval that we can look at that contains the initial value so that we have an actual unique solution for our differential equation. Yeah. F is like just an expression that has x's and y's in it. Let's see. Well, what you have in a given doesn't have to be in a conclusion. So f is some function. So let's see if we can come up with an example. So let's take a look at y prime plus x times y is equal to 0, something like that, for example. And so let's identify a point. I don't want to mess around with any zeros. So let's just say at 1, 1. So this is equivalent to saying y of 1 is equal to 1. Maybe let me change one of them to 2. So this is your initial condition, and that can be translated as a point on the xy plane as a 1, 2. So what they expect you to do, or the way they want you to think about this, is to get y prime by itself, and then now this is your function f of xy. And it looks like on some interval that contains x is equal to 1, this looks like it's pretty continuous. So now this partial derivative is the derivative of this function, this negative xy, with respect to y. So just a little calc 3 thing going on here. What's the derivative of negative xy with respect to y? Negative x. You treat the other variable as if it was a constant, like it was 5, and take the derivative of negative 5y with respect to y, so that's just 5, and just replace it back with x. So this function and this function are both continuous on some interval that contains 1. In fact, it looks like it's continuous for all real numbers, so if you just put all real numbers there, then that includes 1, so we're all good. So then there exists an interval around 1 that contains AB, whatever that AB where it's continuous, well, minus infinity to positive infinity, so that we can find an actual solution to this. So all this is saying is that there exists a solution. There exists a unique solution to this initial value problem. So we can find a solution, and we can say that's the only solution for this particular problem. Okay? So this looks like another separable differential equation, which maybe this will be our second example when we get there of solving it. Right now, we're not interested in solving it yet. I don't know. Maybe you're interested in solving, but let's keep the suspense going. Let's have you at the edge of your seat. Are you guys at the edge of your seat? I'm at the edge of mine. Yeah, so the initial condition can be translated into a point if we're talking about one first order, if we're talking about a first order differential equation, yeah. Yes. Yeah, so let's break down the pieces here with respect to this term that we're looking at. So this is x0, y0. This is your f of x, y. This is your partial of f with respect to y. And they're continuous on R. So that's the conditions. Conditions is that you want this differential equation to contain this point. The solution contains this point, and then you want your f of xy, which is the result after you solve for y prime by itself, and the partial of that function with respect to y to be continuous on some interval. In this case, the interval is all real numbers. So if that's the case, then the conclusion says that there's going to be a function that has there's going to be one function that satisfies this differential equation and this initial condition. Oh, it wouldn't satisfy this theorem if like this thing was not defined at something. So if we put a 0 in the denominator or something, that there might be an issue. Yeah, but some of those are, yeah, they get kind of weird examples. Any questions? Yeah. Usually not. This is one of those theoretical things that are just here for theory's sake, and it won't really affect. There might be some special cases. I probably won't throw it in a quiz or homework, or in a test. But there might be some special cases in the book where they tell you that this doesn't satisfy this theorem. Yeah. That could work. Yeah, so we might not have a solution. I was thinking something simpler where a 0 would be bad, like the logarithm or something, or one of the tangent functions where it goes off to infinity. So like the tangent is one of those functions that so y prime minus tan x y or something like that is equal to x. I don't know, something weird. In any case, then your f of x, oh, and your initial conditions say at 0, comma 5. So this is, no, tangent exists at 0. Let's try, where is tangent bad? Pi over 2. Now let's change this to pi over 2. Yeah, just, yes, it does. Okay. Sure. Anyways, we're looking for something bad to happen. So if you put 0 in for x, then the cotangent is going to be undefined. So we have, if this is your point, your initial condition, and you're saying y prime is equal to cotangent of xy plus x, then this is like your f of xy. And this is not defined at x equals 0. So we're going to have an issue here where it doesn't exist. It's definitely not continuous. It's not defined there, so it's definitely not continuous. Not continuous, or f xy not continuous. So if it doesn't satisfy the given parts of the theorem, then we can't make the conclusions. So no guarantee. For a solution. So this could be one of those things. We don't say the theorem fails. We just say the theorem doesn't apply because the condition's not satisfied. All right. There could be. In this case, there isn't, because it's not defined there. So if it's not continuous, something like with an absolute value and there's a break in the derivative or something like that, it might still, the solution might still exist, but if it's not even defined there, it probably won't happen. Yeah. No, well, this then doesn't meet the conditions. There's still a possibility. So the if-then is kind of funny. This is an if-then kind of statement. And so if it satisfies the condition, then it has to satisfy the conclusions, period. If it doesn't satisfy the conditions, then, well, maybe, maybe not. There's no guarantee. All right. Before we move on to the next section, let's introduce ourselves to a possibility of running into one of these types of problems where we're not looking at something happening in the initial condition, but rather something happening on one side and on the other side of two different x values or two different values for the independent variable. And that's called boundary conditions. So, sometimes you might be given a problem like this, and we'll see a couple of these problems come up, and I don't know how much I'll stress this in our quizzes and exams, but sometimes you have some information about what's happening on a couple of points, and this would probably work more on like higher order differential equations and usually second order differential equations. So sometimes we have that spring problem that we're going to dive into later on, where you can see this thing oscillating, and then it has information not about what happens at the very beginning, but maybe the position in the beginning and the position at the end, or the derivative at the beginning, the derivative at the end. So those are possibilities to describe what's called a boundary condition. So boundary condition are conditions given on two separate points. So let's take a look at this particular problem here. We got y double prime plus y is equal to 0. And then an initial condition would maybe have like y of 0 is equal to this and y prime of 0 is equal to that. But here, you have two different x values that you're considering, and so that is now considered a boundary value. Now the boundary value problem, the boundary conditions can be given as a function or given as a derivative, or actually technically it could be given as a mixture of the original function and the derivative. So solving for this is the process will be close to being the same. I'm wondering if anybody can come up with a solution to this. With the boundary conditions. Yeah. So I wonder if we can find a solution to this. So the thing about the existence and uniqueness theorem, that applies to initial conditions, initial value problems. It doesn't necessarily apply to boundary value problems. In fact, for boundary value problems, you might be able to find a solution that is not unique. So that already is different from the existence and uniqueness theorem, or you might not be guaranteed a solution even if you satisfy those conditions. You have a solution? Yeah, just for this function. Y equals, let's see if that works. -4. Let's see if that works. I need two derivatives, right? So the first derivative and then the second derivative. So we have to add these two and come up with 0. I don't know. Is that right? Oh, just get 2. Is that right? So y double prime plus y, is that equal to 0? 2 plus, I don't think so, right? We need a function whose second derivative is itself. What might those be? Yeah. A sine, just a period maybe. So we need a period and a shift. Oh, that looks really complicated. Well, I don't know. Do you guys remember any special types of solutions that we talked about yesterday or 2 days ago? The trivial solution? Will that work? Yeah, that'll work. Well, it looks like it'll work, right? That. Oh, yeah. So that's a different problem. So those are two different examples. All right. In any case, yeah. Well, we can't apply the uniqueness theorem for this, but if we're talking back at the initial value problems, then yeah. Anyways, it's one of these special cases where only the trivial solution exists. So boundary value problems don't guarantee a solution, and if you get a solution, it's not guaranteed that it's going to be the only solution for that particular problem. So it is introduced though because it does come up every now and then, and we will take a look at it when we get to the higher order differential equations in chapter 4 or 5. All right. Examples from text. 1, 11. I don't know if I'm. Let's take a look at the textbook, see if we can find some examples. That's number 11. $15. All right, let's do number 11. So we have a two-parameter family solutions for the differential equation. They want us to find a solution for the second order IVP consisting of the differential equation and the initial condition. So we're going to go back to an IVP example where we're supposed to be guaranteed that a solution is going to exist and it's going to be unique. So here's our differential equation. And this is our considered solution. And these are our initial conditions. So the idea is that you get to start off with a differential equation and an initial condition, so that both of those together is called an IVP, initial value problem. And then you work to find a solution. In this case, we didn't work to find a solution. They gave us a solution. So in our solution over here, y is equal to c1 e to the x plus c2 e to the negative x. We see that this is a general solution. It's a general solution, and they actually mentioned that it's actually a two-parameter solution because you see the two arbitrary constants c1 and c2. Now, if you want the particular solution, the one guaranteed solution that you would get out of this, you would need to make sure that it satisfies this differential equation. Okay, so let's see if it satisfies this differential equation. It does, because they say it's a solution. So now what we want to do is we want to figure out if we want to make sure that this fits the initial conditions. All right, so it looks like we're going to need maybe the first derivative, because that's part of the initial condition. So y prime. The derivative of e to the x is itself. The derivative of e to the negative x, e to the negative x is negative e to the negative x. So this is our derivative. And so we're going to plug the initial conditions in. So we know when x is equal to 0, your y is going to equal to 1. So given that, we have c1 e to the 0 plus c2 e to the negative 0. And this is going to give us 1 is equal to c1 plus c2. And then dealing with our second initial condition, when the derivative is equal to 2, then x is equal to 0. So the derivative is equal to 2. You got c1e and x is equal to 0 minus c2e negative 0, which is 0. And e to the 0 is 1. And so now we have a system of linear equations. So if you were in a linear algebra class yesterday, you should know how to solve for this, right? So let's solve for this. It looks like we could just add them. I'm going to get 3 is equal to 2C1, and then the C2's cancel, and then C1 is equal to 3 halves. C2 is equal to negative a half. And then so now, from your general solution, you can come up with your particular solution. And that is going to be C1 is 3 halves, and C2 is negative 1 half. So this is your one guaranteed unique solution for this initial value problem. Okay? You guys will eventually understand my handwriting, maybe mid-semester or so. It says particular, yeah? What? Yeah. I don't know. Yeah, so the general solution, well, the thing is that it's a second order differential equation, so you're probably going to want 2 parameter family of solutions for your general solution. Yeah. Yeah, if that was the case. In this case, it's not, so that's why it's even more important to make sure that you have the 2 parameters. All right. So you'll run into more interesting problems when you start doing the homework, and I hope you guys are able to log into Canvas and then WebAssign and at least take a look at what's out there. And do we have homework due this Sunday already? Did you guys look? Oh, so you guys got some time. Don't put it off. All right, let's, I think we're done with this section. Yay. Oh. I don't want to do this. You know what? You guys figure this out. I'm going to skip it. Well, that's it for chapter 1. Maybe I shouldn't skip it. Anyways, the big deal is that whenever you hear a rate of change, you got to think of derivatives. So maybe I'll just put it in the notes and then you guys can figure it out. Wow, a lot of them. Oops, it went past the page. Let's see. There it goes. All right, so the idea behind mathematical modeling. I think I was talking about mathematical modeling in one of my classes, and they thought, is that like, well, they thought it was modeling, like clothes and stuff. No, it's not that. All right, so these are word problems. So you're essentially trying to translate the words into mathematical equations, in this case differential equations, and then when you do that, in this case they just want you to come up with the differential equations. They don't want you to solve for it because we have no tools to solve for it yet. So maybe at the end of the second chapter, there's more modeling there to do. So let's have you guys try to figure out this modeling here on your own, and then when we get to the applications in chapter 2, then we'll dive into the idea of translating. But let's jump to the next section. Nope. My oh, I really want to do separable differential equations. Maybe I'll do separable. No, we have time. So maybe I'll do section 2.2 first, and then I will come back to 2.1. Just so we can say we actually solved some differential equations today. And we'll get to take a look at those equations that we were looking at earlier, or have something similar to that. So a first order differential equation is said to be separable if somehow you can separate the x's and the y's as different factors. And before we do an example, let's do one example of a separable differential equation. And this is the example that we saw earlier. And usually, to be able to visualize the idea of separable differential equations, we want to write our derivatives in Leibniz notation so that we can see the separation happen. And then we had another example where we had y prime is equal to, or y prime minus xy or something like that, plus xy is equal to 0. So this is another one where we can say dy dx is equal to negative x times y. And so if we can separate it, then it's separable. And just to give you an example of something that's not separable, in terms of trying to factor things out, you cannot separate these things. So an example would be y prime equals y plus x. There's no way you can separate it as two different factors. Now we have two different terms, but that doesn't count as factors, right? So we're not going to be able to solve for this differential equation using the techniques for separable differential equation. Do you mean solve for this? Sure. But don't you think it would be good to figure out what you can't do? We're going to get there. Yeah. We're going to get to the technique, but I think it might be a good idea to figure out what's not separable and what is separable so that you're not looking at this and trying to use a technique that we're learning. All right, so let's solve for one of these. It looks like we have 3 examples now. Let's solve for the example they gave us. And we have dp dt is equal to 0.15 p plus 20. And let me write it like this for now. I have a p of t there, but let's ignore the p of t. And the idea behind the separable is to take your Leibniz notation and bring the d's to one side, the dp to one side, and the dt to the other side. So if I take this dp and bring everything with a p to one side, the left side, so I have this whole thing that I probably need to divide. And then on the other side, I would have dt. All right. Now it's separated. So that's the idea behind separable differential equations, is to be able to separate it like this. And then now the differentials are already kind of written there for you. So you can probably just, I don't know, just take the integral of both sides. So the integral of the left-hand side, if you do some appropriate u substitution, it'll be the ln of 0.15 p plus 20. And there's, because of the u substitution, you got to divide by whatever. And then on the right-hand side, you have t. Yeah, what about that? Now there's a constant that would come out on the left side integral and a constant that would come out on the right-hand side integral. So we just bring it to all to one side. And so the c actually carries a constant from these two. Okay. Now this is an implicit solution. Remember implicit? How can I make it explicit? What would I need to do to make it an explicit solution? Yeah. Yeah, we're solving for p of t. So if we get p by itself, then we can get an explicit solution, which is generally what we want. And if there's any chance of doing that, you should do that. Otherwise, it stays implicit. In this case, yeah, we could do that. I think we need to multiply by 0.15. Now, there is a parentheses that should go around the t plus c, right? But then if you distribute that, the c times 0.15, that's just another constant. Actually, let's make it explicit. We can replace a constant times an arbitrary constant as just another constant. So now, if we, this is power. Don't have to, but I suppose we can. So Another move that's usually made in these types of differential equations is that they take this constant, because it's just another constant, right? We just did one more thing to this constant, so it's just another constant. And sometimes they just call that A, or A naught, or P naught, or whatever, and just say A e to the 0.15t. Because it's just a constant. Well, that wouldn't be included as part of the constant, right? Because the constant is e to this thing, and if you add something to it, it's not the same as combining it. And so a couple more steps. I think we need to add or subtract the 20, and then we need to divide by a 0.15. And then now I have P of t is equal to this. And now P is by itself, and now I have an explicit solution. Okay? Not quite done yet. So this is a general solution. It has an arbitrary constant, so it's a family of solutions. And according to our existence and uniqueness theorem, if we have an IVP, if we use our initial condition, then we're not going to have a whole family of solutions. We're only going to have one particular solution. So let's use that initial condition where when t is equal to 0, p is equal to 100. And then we'll plug in those values. And then solve for the arbitrary constant. So e to the 0 is 1. I have 100 equals 1 over 0.15. And then I have a minus 20 in parentheses. So let's multiply this by 0.15 on both sides. Is that 15? And then a is equal to 35. So now we can write our particular solution, P of t is equal to 1 over 0.15 times 35 e to the 0.15t minus 20. And then now we have our particular solution. Okay. All right, we actually solved our differential equation here. That's exciting. So let's see if we can come up with another example. I mean, we have these examples. And let me see if I can come up with an example from the textbook. Separable. Ah, look at that. Pick a number between 1 and 25. So we have to first identify if it's separable. Well, let's just say it's separable because we got it from the separable differential equation section. And then after we do that, let's see if we can put it together and take it apart. And so I think the first move that we should probably try to do is bring everything on one side except for the dy dx. So you get dy dx, and you have 1 over x squared. And good thing that x is okay to be 0 here. Your interval should contain -1. And then y minus xy. Now, it's not quite separated yet. Any ideas to try to separate this? Yeah? Factor out a y. Y over x squared 1 minus x. All right, so you could decide what to keep and what to leave. It looks like there's a y over here. So it looks like I want to separate it. And in general, you want to keep put the dependent variable on the left side and the independent variable on the right side. So if the dy stays on this side, this y, which is up in the numerator, can go over as a denominator on the left-hand side. And then everything else here, we got 1 minus x over x squared with a dx. So now you have to integrate. What? What? Sometimes. Oh boy, now what? Oh, there it goes. What? So, if we're dealing with this, we have probably want to separate it, and then we integrate both sides. And then we get ln of y, and then we have minus 1 over x, and then another ln x, and then plus c. So we can find this explicitly. So here are a couple of tricks to deal with the initial conditions. One way to do this is to go ahead and solve for y, so that you have an explicit expression of y, and then plug in the initial conditions. The other option is to plug in the initial conditions now and solve for c, and then after you find c from this point, then you can solve for the rest of them. Okay, so let's try that. Let's put in the value for x is equal to -1 and y is equal to -1 for this particular problem, and then solve for c here, and then put it back into c here, and then solve for y. So ln the absolute value of -1 is equal to -1 over -1 minus ln absolute value of -1 plus c. See what happens. What do we get? So c is equal to -1. And then so now let's put that back in. Ln of the absolute value of y is equal to -1 over x ln minus ln of absolute value of x minus 1. Now we need to solve for y, so raise this as a power of e. And you could probably simplify this a little bit more. E to the -1 over x times e to the negative ln x times e to the -1. They're all negative. What? As what? What? This is minus x. What? Oh. Logs. The negative in front of the ln goes as a power of x. So it's e to the ln of x to the negative first power. You guys know algebra, right? And then we have e to the -1, and then we have e to the -1 over x. So y equals 1 over e to the e times, you can combine this too, but we're out of time, so I'll just leave it as that. So this is your particular solution, the unique solution to your initial value problem. All right, so I'm probably gonna, on top of your regular assignments, I'm probably gonna assign things for you to try to prepare for class. And so I'll send messages, announcements over the weekend to see if there's anything that I'd want you to do before coming into class on Tuesday, okay? Otherwise, you can try to get started with your homework. Homework's available already, and it's due not this Sunday, but next Sunday, or the Sunday after that. All right, have a good weekend. Hello. Oh, I don't know. Just log in and see what happens next week.